begin our discussion by talking about chemical spontaneity. In particular, we're going to begin spontaneity at constant temperature and volume. And what we have learned so far is that the increment of change of entropy in the universe is greater than or is equal to 0 for any process which occurs spontaneously. That was the premise of Clausius in the Clausius inequality. Well, if we partition the universe up into the system and surroundings, then ds of the system plus ds of the surroundings is greater than or equal to 0 for a spontaneous process. Now, if we go to our surroundings and make the definition, of course, that the change in entropy of the surroundings is solely dictated by what occurs in the system, and we will substitute for ds surroundings minus dq system over t. So we have ds of the system plus a negative dq of the system, because remember, the heat is exchanged with the system. So if the system undergoes an exothermic process, the surroundings undergoes endothermic. If the system undergoes an endothermic process, the system undergoes exothermic. So the sign is negative between the two. So I have the inequality that I see written there. And now let's recognize that if I specify the conditions under which the process is prepared, and let's specify that we have a system at constant volume. And at constant volume, we know that the PDV term is 0, so du is equal to dq. So I can replace dq of the system with du of the system, and I get ds of the system plus a negative du of the system over t must be greater than or equal to 0 for a spontaneous process. Now what I'm going to do is just multiply through by t. Then, if you like, I can either flip the quantities to one side or the other. Notice how I have a greater than 0 inequality. Now I've switched it to a less than 0. That's because you'll notice I flipped the signs. I took everything that was negative and made it positive. So if the left-hand side is greater than or equal to 0, the negative of it would be less than or equal to 0, if you like to think of it that way. So I get that du of the system minus TdS of the system is less than or equal to 0. Now what was done by Helmholtz is the definition of a new quantity, the work function as it is often known, and we will call it the Helmholtz function. And it is defined as A equals U minus TS. And then if I take the differential of that, I get that dA is du minus the product of the differential of TS, which is TdS minus SdT. Now if I specify not only a constant volume situation, I also specify a constant temperature situation. The SdT term goes so that dA equals du minus TdS. And that is, as you can see, the expression that I had above. So what we're getting at then is that for a spontaneous process, as long as the temperature and volume are constant, we have this new defined work function or Helmholtz function. And if this dA of that function is less than or equal to 0, I have a spontaneous process. Now this newly introduced quantity A has the same kind of very important and familiar properties that we've seen with our other thermodynamic functions. First of all, it is extensive or scales with the amount of matter present. Second of all, it is a state function, which of course means that the integral or the differential dA is exact, meaning if you integrate it between some limits, you only need to know what those limits are. So the integral dA is always equal to delta A, independent of the path between the final and the initial states. Let's try to get a little bit of insight into a broader significance for this Helmholtz function. Again, if we start with the universe being partitioned into a system and surroundings, And then again for the surroundings, let's substitute minus dq the system over T, which is how we can measure the entropy of a system when we deposit some heat into a system into a surroundings from a system. Okay, so what we can then note is that this has to be greater than or equal to 0. So that says that the increment of change of entropy in the system must be, by moving the second term to the right, must be greater than or equal to the increment of change of the heat of the system divided by the temperature. We multiply both sides by T, and we get that TdS is greater than or equal to the dq for the process that's going on. And now let's substitute the first law in there, and which would say du is dq plus dw, so dq must be du minus dw, so that TdS must be greater than or equal to the increment of change in internal energy minus the increment of change of work. So what we then simply do is a little bit of rearrangement. So we write dw is greater than or equal to du minus TdS. Now remember, du minus TdS was the definition of what we called dA. Now what we can then note is a couple things there. We have dw is greater than or equal to du minus TdS, which is greater than or equal to dA, but we also note that dw max would be the maximum work that we could harvest out of this. And if work is done by the system, then work is negative. So in that inequality, the biggest possible value of a negative work will be when the equality sign or equal sign applies. So dw max, the maximum work you can get, would be equal to du minus TdS. And if we then integrate that function, what we see is that the maximum work you can get in a constant volume isothermal process is when is equal to the change of this Helmholtz function. So this Helmholtz function is telling me, again, at constant temperature and volume, just how much work it may be possible for me to extract in and during that particular process. Constant volume processes are nice, but as we have oftentimes discussed, the more germane or more relevant type of situation that we deal with in everyday life is a constant pressure process, because whatever we do on this planet, we have to deal with the fact that we're always under the auspices of the atmosphere pushing upon us. So if instead, again, we begin with the Clausius inequality and we partition the universe into a system and surroundings, nothing different, then just as before, for the surroundings, we substitute minus dq the system over T. And now, instead of looking at this from the constant volume perspective, I'll look at it from the constant pressure perspective. And the heat exchanged at constant pressure is the enthalpy of the system. So then I have the ds of the system plus a negative dH of the system over T must be greater than or equal to 0. Again, just like we did for the Helmholtz function, I'm going to multiply both sides by T. Then if I just take the negative of the left-hand side, it will be less than or equal to the right-hand side, or I could just move the things on the left to the right, the things on the right to the left, and do anything I want, but now the inequality is reversed. And I will again define a new thermodynamic function. This time the function I will give the symbolic representation g. Now, unlike the Helmholtz function where different people use different symbols depending on who is doing the discussions, g is universally used for this function. G is known as the Gibbs function after Josiah Willard Gibbs, probably the greatest American scientist you never heard of or you vaguely heard of. But we will define this quantity as G equals H minus TS. And then you will note that if I take the differential of change of G and use the product rule, that dG is dH minus TdS minus SdT. And then what I'm going to stipulate, in addition to the constant pressure restriction, I'm going to institute a constant temperature restriction. So then the increment of change in the Gibbs function is equal to dH minus TdS. And you'll note that is the function on the left-hand side of the constant pressure expression above. So we can substitute that in, and we note that for a spontaneous process that is occurring at constant pressure and temperature, that this Gibbs function has an increment of change that is less than or equal to 0. Now remember, it's less than 0 for normal irreversible processes, and it is equal to 0 for reversible processes. And what, again, in chemistry is the most familiar reversible process? It is the equilibrium process. You're at the tipping point where it could literally switch either way at any instant. So dG is less than or equal to 0, the increment of change of the Gibbs function at constant temperature and pressure, where we typically will deal with the things we do in a laboratory. So it turns out that this Gibbs function is much more utile than is the Helmholtz function, for the simple fact that it's designed to be in a constant pressure environment rather than a constant volume environment. A couple other things, much like other thermodynamic quantities we have encountered, the Gibbs function is extensive, scaling with the amount of matter present. And then, of course, the Gibbs function also is a state function, which means if I want to look at the integrate, sum up infinitesimally the increment of change in dG between some limits, then it doesn't really matter how I get between the limits. All I need to do is do a definite integration and subtract those boundary conditions of GF and GI, so that that integral is delta G, independent of how I get between GI and GF. Now, before we end this discussion here, I must mention to you the fundamental importance of Gibbs. He was an American scientist at Yale University in the late 1800s. Did many important contributions in thermodynamics, also in statistical mechanics, the basically nanoscopic treatment of thermodynamics, very fundamental and important contributions there. And he actually did fundamental important contributions to the science of just basic physics by the introduction of vectors. Before Gibbs's notation of the modern vector and the idea of dot products, curls, and all those other cross product things that we do with our vectors, vectors were treated in physics in a very cumbersome fashion. His elegant treatment of vectors is probably his most fundamental contribution to pedagogy. No question about that. Like we did for the Helmholtz function, let's probe a little bit into the deeper significance of the Gibbs function. We'll begin with our definition G equals H minus TS, and then take the increment of change using the product rule. dG equals dH minus TdS minus SdT. Then what we will do is substitute the definition of enthalpy and the definition of internal energy into that expression. So we'll put in the dQ plus dW plus PV for this combination of factors, and we get a big long expression that you can easily verify is true. Then what we will do is we will state that we had constant pressure, so that dP is 0. We'll state that we had constant temperature, so that dT is 0. So this is a constant pressure, temperature environment, very commonly what we experience in a laboratory. So that then dG is equal to dq plus dw plus pdv minus TDS, a whole bunch of terms. And another thing that we typically do in a case like this is we first say we're going to do this reversibly. Now notice I didn't put anything about the difference in dg from the reversible to the non-reversible case because dg is a state function. Doesn't matter if I choose the path reversibly, if I choose the path irreversibly, dg is the same. It's path independent, so I don't really have to indicate that. However, work is a path dependent function. So once I specified a path, I've specified a way in which dw is prepared. It's not independent of how the path is chosen, so I have to be a little careful at that point. So now what I'm going to do is I'm going to note then that I have my cancellation of my TDS terms, and I get dg is dw reversible plus pdv. And if I partition this dw reversible into all the possible kinds of work that can be done, of course, generally speaking, and almost entirely we've been talking about gas expansion work, but recognize there are many other forms of work available, and in particular, one important case is electrical work. Turns out, particularly in life sciences, that's the important type of work we can generate upon respiration and metabolic processes to power our muscles through electrical stimulus and things of that sort. So if dg is dw non-expansion plus dw expansion plus pdv, and then we put in for the expansion piece of work minus pdv, we get a cancellation of those terms. And we see that what the Gibbs function is very importantly representing is the non-expansion work. This is why, ladies and gentlemen, you often hear the G value called the free energy. It is the free energy because after expansion work is taken care of, where the atmosphere is in the way and things have to be done with the atmosphere in terms of it pushing back upon us, that of course is a cost of some of the energy of a particular process which is occurring. Well, the excess energy is what is available to be used by a system. It is the free energy. It is what you can harvest and use beyond what you have to pay the piper of the atmosphere for. Further explore the idea of this Gibbs free energy and its connection with spontaneity. Again, we first begin with the definition G equals H minus TS. Then I will take the increment of change of that and specify at constant temperature. The SDT term is gone, so dG is dH minus TDS. Then I can integrate both sides of that equation over a bunch of state functions. Okay, and again, we're specifying constant temperature, so the T is pulled outside of the integration. And again, since everybody is a state function, we get a very familiar expression that biology people employ all the time and also freshman chemistry uses, and that would be that the change in Gibbs function is equal to the change in enthalpy of a system minus T times the change in entropy of that system. Okay, so notice essentially what we're doing here is I'm measuring the free energy change in a system as a function of the enthalpy change of the system and the entropy change of the system. And again, remember, if delta G is less than 0, we have spontaneity. If it is equal to 0, you are at the magic point of reversibility, which is, we will from now on just recognize we're at equilibrium. When delta G equals 0, that'll be a very important trick we will employ in chemistry. And if delta G is greater than 0, simply all that you're saying is that you're attempting to run a process in the exact opposite direction of its spontaneity. If we reverse what are the products to the reactants and reverse what are the reactants to the products, then of course GF becomes GI and GI becomes GF. And if delta G for a particular direction is greater than 0, then by reversing everything, delta G of that situation is less than 0. So when you get delta G greater than 0, you're just saying that the process would be spontaneous in reverse. Now, of course, we know exothermic processes have negative enthalpy, endothermic processes have positive enthalpy, randomizing processes have positive entropy, ordering processes have negative entropy. So then we can collectively look at how processes will influence the sign of delta G. If you have an exothermic process that is creating disorder in the system, so that then my delta H term is negative and my minus T delta S term is also negative, we would find these are always going to be spontaneous. And an example I can offer for something like that is a nuclear decay. These are exothermic things which are breaking nuclei apart. They are completely temperature independent. They occur no matter what the temperature of the situation happens to be. If you have an endothermic process, which is causing order in the system, endothermic means delta H is greater than 0. An ordering process has negative entropy, and since the T delta S sign is got a negative in front of it, negative means that term is positive also. So endothermic processes ordering the system are not spontaneous at any temperature. Temperature can't help you get those to occur. And I can't think of any, at least naturally occurring things, because there are no such things. Now then, the mixed bag cases where the spontaneity is going to be true if delta G is negative. And if we have one of the terms, delta H or T delta S positive and one negative, then it depends on which one is winning, whether or not delta G will be negative or positive. So in our third case, an exothermic process that creates order in the system, the delta H term is negative, but the minus T delta S term is positive. So if I want the overall delta G to be negative, it's only going to happen when the delta H term is more negative than the negative T delta S term is positive. So that will only occur below a certain threshold temperature. Now, in the fourth case, we have an endothermic reaction which is causing disorder. The endothermic thing makes a positive contribution to delta G. The disorder with a minus sign in front of the term makes a negative contribution to delta T. So the negative term is what we want to dominate, so that delta G is negative, and that will occur above a certain threshold temperature. So these are things which will occur spontaneously when you reach certain beginning temperatures, and then anything over that. Let's look at the case of the application of Gibbs' idea of spontaneity to the evaporation of benzene, C6H6 liquid becoming C6H6 gas. I can find NIST values for the enthalpy of formation of liquid and gas phase benzene. I can find NIST values for the entropy of formation of liquid and gas phase benzene, and I want to find what temperature above which the process C6H6 liquid becomes C6H6 gas. I calculate delta H as the products minus the reactants, and I do that for 1 mole. Calculate delta S as products minus reactants, do that for 1 mole, and then I see that this is an endothermic process creating disorder. So can I predict there should be a threshold temperature above which this is spontaneous? So can I predict that? Well, I will take my delta G equals delta H minus T delta S and find the temperature where that is spontaneous, so that function must be less than 0. I will divide, I will move the T delta S term to the other side, and then I will divide both sides by the delta S. So delta H over delta S is less than or equal to T, or I can reverse that. The threshold temperature above which this is spontaneous will be greater than the temperature calculated from when I divide the entropy value for the reaction into the enthalpy value for the reaction. And when I do that, I get that T is greater than 80 degrees C. And it turns out that the normal boiling point of benzene, the temperature at which liquid benzene spontaneously becomes vapor benzene, is 80.1 degrees C. So we see this is a very good indicator of such things. Now let's take a very important step in our discussion and understanding of thermodynamics. That is when we take the first law and second law and combine them together. So let's begin with our internal energy statement that du is dq plus dw, and then for our dw term we will substitute what we have learned about we have expansion type work being done by a gas. So we have dq minus pdv. Now, if it is reversible, then of course the internal and external pressure are matching exactly, and then we will substitute into this expression our second law value of the entropy, and that is that ds is equal to dq reversible over t. So when I put that in for my dq term, and I have my pdv for the work term, I get that du is equal to dq reversible over t, and for dq I multiply both sides of my equation for entropy by t, and so dq is tds. So the increment of change of the internal energy is tds minus pdv. And even though I discussed this in terms of it being a reversible case, since du is a state function, it is path independent, I can remove the restriction of it being reversible or irreversible. It doesn't matter how I get through the increment of change du. I'll have the same increment of change in du no matter which way I do it. So I can remove any inference to this being designed reversibly, and I can just globally say that for any process, reversible, irreversible, whatever, that du is equal to TdS minus PdV. Now, what we will claim is that this is the combination of the first and second law, and very often this is magnanimously referred to as the fundamental equation of thermodynamics. Because what we will see is what we're now claiming. Before we said that the internal energy was a function of the temperature and the volume of the system. Here, what we're claiming is that the internal energy is a function of the entropy and the volume of the system, not the temperature and volume of the system. Okay, so again, this holds generally to any material, really not meaning that it has to be a gas phase process. It holds to any phase of matter that a system might express itself in. It holds for reversible processes, irreversible processes, whatever I choose to study. Again, we're going to now spend a great deal of the rest of our discussion looking at the implications of this combination, first and second law, or fundamental equation of thermodynamics. Apply what we've learned about the fundamental equation and its application to the internal energy. Let's now apply the fundamental equation to all of our other familiar thermodynamic quantities. So let's start with, how does the fundamental equation of thermodynamics change our perspective when we think about the enthalpy of a system. Now the fundamental equation, the combination law I've written there, du is TdS minus PdV. Now we'll go to the definition of enthalpy, which is H equals U plus PV, and we'll find its increment of change by using the product rule. So I get dH is du plus PdV plus VdP. Now all I will do is substitute into that expression our newfound combination law for du, and I get TdS plus minus PdV plus PdV plus VdP. And what I now see is that I have redefined the enthalpy, which before I said was a function of temperature and pressure. Now I can more fundamentally state that an increment of change or the function of enthalpy is a function of pressure and internal energy of a system. So let's now see how we can do the same sorts of things to our newly introduced thermodynamic quantities. Let's look at what the combined first and second law has to say about the Helmholtz function. Again, the idea we will begin with is our so-called combined law. du is TdS minus PdV. Then we'll take the definition of the Arbeit or work function or Helmholtz function, whatever I want to call it. That was A equals U minus TS. Getting ahead of myself, because what I'm going to do with A is I'm going to find its increment of change using the product rule. Then I'm simply going to substitute in my combination first and second law for the increment of change of the internal energy. I'll notice I get a cancellation of the TdS terms, and so I can conclude that the increment of change of the Helmholtz function is equal to minus PdV minus SdT. So now what we're saying is before we looked at the internal energy as being a function of volume and temperature. Now in the idea of entropy, with the idea of entropy being introduced, we see that the increment of change of the Helmholtz function is a function of volume and temperature. Now this turns out to be something we can control a little more easily in the laboratory than we can control the previous ones. Remember, we saw that the internal energy was a function of the internal energy was a function of entropy and volume, and the enthalpy was a function of entropy and pressure. So in what ways can we use expressions like that? Well, we'll have to look at some applications of them coming forward. Let's introduce the combination thermodynamic law into our friend the Gibbs function. Here we will begin with the combination law as it applies to the enthalpy, dH equals TdS plus VdP. Then we will use the definition that G is equal to H minus Ts and look at its increment of change from the product rule. dG is equal to dH minus TdS minus SdT. We substitute dH from above into this expression, and we get that the increment of change of dG with the cancellation of the TdS terms is equal to VdP minus SdT. So what we're learning now with the introduction of entropy is that the Gibbs function is truly a function of pressure and temperature under this representation. This is going to turn out to be very important for us because, of course, our most controllable aspects of experimental design are pressure and temperature controls. Real utility of the fundamental law of thermodynamics comes when we hit it with a bunch of mathematical tricks. So we've talked a little bit about these mathematical tricks that we're going to employ here before, but let's remind us of their general premise. Let's consider I have a dependent variable f that is a function of two independent variables x and y. So essentially I could make a plot of how f varies as x and y vary. And we've talked about this before. If I want to know how f changes with respect to changes in y, I will go to the fy plane of my graph. I will hold x plane fixed. I won't let any variation occur in the x plane. Then an increment of change of f in that plane is the slope of the function times the increment of change of y. Remember, the slope in that plane is delta f over delta y. So if I want to know delta f in that plane, I will take delta f over delta y times delta y. Now I want to know how the function f changes as x changes. I will hold y fixed, meaning I will move into the xf plane. No variation in y. The slope in the xf plane is delta f over delta x. And if I want to know how f changes with respect to x in that plane, I will take that slope times the increment of change delta x. So delta f in that plane is mx times delta x. So if I combine those two, I get that the total change in f is equal to holding the function in the x plane fixed while I vary it along y, then holding the function in the y plane fixed as I vary it according to x. Now you say, how can you get away with this? Well, I can get away with this because x and y are independent variables. It's just like our coordinate frame. If I'm looking at z, x, and y, I can march along in the x direction, halt, then march along in the y direction, and I get to the tip of the arrow independent of the change in x with the change in y. These are independent variables, so I can get away with that. So the increment of, instead of doing this in a finite sense, let me do it infinitesimally. Instead of delta f of x and y, I'm going to look at df x and y. So it will be equal to the increment of change in each plane, and that increment of change is now the continuous slope of the function. In the fx plane, it's df dx. In the fy plane, it's df dy. But I'm constraining it such that while I'm looking at the increment of change in the x plane, there's no increment of change in the y plane, and vice versa. So if I multiply this slope by the amount of change, I will get the increment of change in each function. So what I can conclude, for an exact differential, and this is true for anything that is a state function, then the increment of change df as a function of two independent variables will be df dx at fixed y times the increment of change dx plus df dy at fixed x times the increment of change in that segment dy. Now, if I had three variables, x, y, and z, I would simply just add a third term on here. It would be df dz, but now being held at constant y and x times the increment of change dz. So I could extend this to as many independent variables as I wish. I would just have to have another partial differential term for each. Now, again, I've talked about this idea of the state function and the exact differential before. In this discussion from here on out, we are going to use this extensively to study a host of interesting thermodynamic applications. Let's look at the implication of the internal energy being an exact differential, a state function. Now, with the new information from the combined first law, that this internal energy is a function of the entropy and volume of the system. So the independent variables are entropy and volume. The dependent variable is U. So using that and the idea that we've now established for exact differentials, then du is equal to the partial of u with respect to s at fixed volume times the increment of change ds plus the partial of u with respect to volume at fixed entropy as the volume varies. So now maybe you should think about maybe what this means experimentally. If you're designing an experiment, I'm looking first at how entropy and varies and how that affects internal energy. We'll have more to say about that means. And we're doing it in an isochoric process. The second partial differential is saying how the internal energy changes as the volume of the system changes at fixed entropy. Now let's think about a little bit about what does fixed entropy mean. Is that an experimentally difficult design that we would have to carry out in a laboratory process? We can certainly envision a constant volume experiment. I just put a rigid container, put a gas in a rigid container and let it do its business, but the walls of the container don't move. So the first quantity, I can envision designing experiments that follow that kind of behavior. But the second one seems a little weird, the change in internal energy with volume at fixed entropy. How can I design experimental processes that are akin to that? Well, all I would have to recognize is that fixed entropy means no change in entropy. That means adiabatic. So if I design an adiabatic experiment, it will be possible that I can now measure changes in internal energy and volume, and that would be the second term in this increment of change of internal energy. Now, let us compare the top equation to the second equation. They line up exactly if I take the partial derivative of u with respect to x at fixed volume and equate it to temperature. So I now have a new definition, and as a matter of fact, this was how Lord Kelvin defined temperature. He defined it exactly in the way that we see right there. Well, as a matter of fact, he defined it in 1 over that. We'll talk about that in a moment, but the change in internal energy with respect to entropy in an isochoric process is equal to the temperature of that system. Again, this is giving a hard definition to exactly what temperature is, and this is literally how Kelvin did define temperature. Again, we'll hit that a little later as well. Now notice if I compare the second partial differential to the top term of the fundamental equation, I would note that the change in internal energy with respect to volume in any adiabatic process is equal to the negative of the pressure of that process. Now, why is there some negative connection there? Let's think a little bit about this. Let's just suppose I have a constant entropy system. That, of course, means adiabatic. That means dq is 0. So let's take that partial derivative then and just multiply both sides by dv. And it would say du equals minus p dv as long as it's adiabatic. du equals minus p dv when dq is 0. Hey, guess what? That's exactly what we've been saying all along with the first law. du equals minus p dv as long as dq equals 0. So this statement holds together with everything else we have discussed so far. Now, notice what the other one is saying. du is equal to TdS if I multiply both sides. And that is true as long as we were at constant volume. And if you were to rearrange that, that would be saying the ds is equal to du over t, which is exactly what we said at constant volume, because at constant volume, dq equals du, because there's no PDV term. So these expressions are really saying nothing more than we have said all along about the connections between internal energy and the mechanical variables P and T. Now, we can do the same kind of game for the fundamental equation of enthalpy. We begin with the fundamental equation, dH equals TdS plus VdP. I now state that H is a function of S and P, and H is an exact differential, so its increment of change should be how the enthalpy varies with entropy as long as I hold the second variable fixed, times the increment of change in that function entropy. Then I go to the other plane and I vary enthalpy with the pressure at constant entropy, and I look at the increment of change in that plane, dP. I sum that together and I get the entirety of change in dH. So dH is the partial of H with respect to S at fixed P, ds, plus the partial of H with respect to P at fixed S, dP. Now if I compare that equation to the equation directly above it, I see that dH ds at fixed P equates directly with T, and I see that dH dP at fixed S equates directly with V. And again, these hang together with earlier discussions we had with the significance of enthalpy. On this slide, we do the same thing that we did on the previous slide with internal energy and enthalpy, but this time we apply the ideas of exact differentials and the fundamental equation to the Helmholtz and Gibbs functions. So I begin with my expression for the Helmholtz increment of change, dA is equal to minus PdV minus S dt. Now I insert that into an expression for treating A as an exact differential. It's the partial of A with respect to V at fixed T times the increment of change dV plus the partial of A with respect to T at fixed V times the increment of change dt. So I make comparison between these two equations, and since they are both true statements, then they must match each other exactly. So I come to the conclusion that how the internal energy, how the Helmholtz function changes with volume at constant temperature will be equal to the negative pressure of the system, and how the Helmholtz value changes with temperature at fixed volume or in an isochoric process is equal to the negative of the entropy of the system. So essentially think of it this way. Suppose I do an experiment where I'm somehow able to measure the Helmholtz energy as a function of volume, and I do a series of isothermal expressions. I plot the Helmholtz energy versus volume for these isothermal experiments. They will have a slope which should be equal to the negative pressure at which the experiments were performed. Okay, let's think about something experimentally with the second partial derivative relationship. I do an experiment where I do isochoric sampling of the Helmholtz energy as a function of temperature. I make a plot of Helmholtz energy as temperature varies, and I do these experiments all at the same volume. The slope of that plot will be equal to negative the entropy of the system that I am studying. Okay, let's finally make an application of the first and second law combination to our newly introduced thermodynamic expression for Gibbs, and that begins with G equals H minus TS. Then with some manipulation, we saw on a previous slide that dG, the increment of change of Gibbs, is equal to VdP minus S dt. Now, treating G as a function of P and T, and knowing that it's an exact differential, it's a state function, I can write it as the slope of the change in the GP plane. If I stay out of the T plane, that's what the first partial derivative is saying, times the increment of change in that p-plane, and then I will add to that. I'll move over and keep the p-plane fixed and go into the gt plane, look at the slope of the function in the gt plane, multiply by the increment of change along the t-axis, and I'll get how g changes as a function of t changing independent of p. And then when I sum all that together, because the variables are independent of one another, I'll get the total change in g. So again, same thing we did before. I'm going to compare that to the expression directly above that, line them up, and I will notice that when I look at the term that's functions of dp, that will be telling me that the Gibbs function changing with pressure at constant temperature says something about the volume of the system, and how the Gibbs function changes with temperature at constant pressure says something about negative entropy of the system. So again, if I were to study Gibbs energy in a constant temperature experiment, and I look at how Gibbs energy changes with pressure, it will have to equal the volume that the system is occupying. The slope of that plot will be volume. If I look at an experiment where I isobaric or constant pressure varied the temperature and looked at how the Gibbs energy varies, I will note that the slope of that plot would be equal to the negative of the entropy of the process. So here's what I would expect in that case. If I'm looking at a solid system, since the entropy of solids is relatively small, the plot of this g versus t will be negative because of the negative entropy, but it will be with only slight slope, so it won't vary dramatically with temperature for a solid. For a gas, on the other hand, gases have large positive entropies, so this will be a large negative value. I would expect the Gibbs function to vary with temperature extremely dramatically, so that I have a big slope of the plot if I'm studying a gas phase experiment, because of its connection between Gibbs and temperature being equated to the slope of that being the entropy of the system. To find the true power of these combination first and second law statements that we've made on the previous two slides, we first have to introduce a few more mathematical tricks. Now, I know many of us are not fans of mathematical complexities of these types, but unfortunately this is just a rite of passage that all chemistry majors have to suffer through, so please just bear with me. And actually, I think maybe after we're done with this, you'll get an appreciation for the beauty of the application of high-level mathematics to these thermodynamic expressions that came about in the 1800s. If you remember way back at the beginning of our class, I explained to you that thermodynamics was really, truthfully, the very first of the theoretical sciences. We took abstract mathematical application to these thermodynamic quantities and were able to make bold predictions of the behavior of systems, even though it hadn't been observed. Prior to this time, science was phenomenological, and I talked about this a lot with you. Phenomenological science means you see it happen, then you try to build a mathematical model out of what you see happening. What evolved at this particular time, in the mid-1800s, with the discovery of all these ideas about thermodynamics and the applications of this mathematics that I'm going to show you now, what evolved was a predictive scientific approach. They were able to mathematically predict the behavior of matter. No one had ever observed it before. They were just able to predict using these complex mathematical tricks. Then what they did was went and experimentally looked to verify these predicted things were true, and they were. This became the hallmark of what science moved and evolved into. The predictive ability of the complex mathematics led people like Einstein and people like not just people like Einstein, they did the predicting, but it led experimentalists to try to verify things that Einstein was predicting for the behavior of the universe and gravity itself, for the things that Niels Bohr and Max Planck and others of that type were describing for the structure of atoms. Nobody had ever seen, or nobody still to this day can see the structure of matter at that level or at the level of the universe itself. But what came about was that people went probing the limits of our understanding after these mathematical models made certain predictions. They went probing for these things and found them. So this is really the case of what's going on here in the middle of the 1800s, the 19th century, the mid-1800s. All these mathematical tools were available. All these ideas of thermodynamics were coming together, and people were making predictions using the applications of the math in order to come to some conclusion as to how the world behaved. Then after they made the predictions, even though many of these predicted behaviors weren't observed, they went and looked and found them. Okay, so let's introduce some of these little mathematical tricks that we're going to use extensively over the remainder of the discussion that we're going to apply to thermodynamics. Let's consider z as a function of x and y. So z is a dependent variable, and it's the dependent variable as the independent variables x and y vary. As we've just talked about extensively here, then the increment of change in z can be found from the partial of z with respect to x at fixed y dx plus the partial of z with respect to y at fixed x dy. This is something that you got to get comfortable with, folks. We're going to be using this, a statement of that type, over and over again in a variety of applications. So now all I'm going to do is just mathematically manipulate that. I'm going to divide both sides of it by dx, and I come to the second expression that you see on my slide. Then what I'm going to do is I'm going to assume that, that this is true in the case where x is constant, so that dz dx is equal to 0. So if dz dx is equal to 0, then I'm specifying that the dy dx that I took on the right is done at constant z. So notice I'm saying, okay, dz dx is 0. That means z is constant. So that means that that dy dx function on the right has to be done. That what we're saying is this equality to 0 holds only if dy dx is evaluated when z is held constant. That's what we're saying by that mathematical application. It has nothing to do with the first two partial differential that were occurring before. Now, if I want that equality of the left-hand side being 0, that is only true when and only when dy dx was evaluated when z was a constant. So now all I'm going to do is rearrange, move the first term on the right of the right-hand side over to the left, and I get this really cool fundamental behavior of partial differentials, which we will from now on call the permuter. And what the permuter tells us is that if you have three variables, z, x, and y, and you want to know how z varies with x as y is being held fixed, and you can calculate that by how the negative of how z varies with y as x is fixed times how y varies with x as z is fixed. Now this mathematical statement over the next few slides we will first verify is true, then we'll see how we can employ it in our thermodynamic discussions, and we're going to be employing it several times over the next several slides. Now I have this newly introduced relationship between partial derivatives of three functions that are related to one another. Let's see if we can apply it in a familiar case. Let's take p V equals nRT, of course, very familiar to us. And let's just set the pressure as being the variable Z, the volume as being the variable Y, and the temperature as being the variable X. So we have a closed system where N is not varying. R is, of course, a constant. But let's now look, how are P, V, and T related? Well, what I'm going to do is go to my permuter and just wherever I see a Z, I'm going to stick in P. Wherever I see a Y, I'll stick in V. Wherever I see an X, I'll stick in a T. And I get that the partial of P with respect to T at fixed volume is equal to negative the partial of P with respect to V at fixed temperature times the partial of V with respect to temperature at fixed pressure. As bizarre as that sounds, let's now just do that process. Of course, P is equal to nRT over V. So dP dt at fixed V is equal to nR over V. You should all be able to verify that that is true. Now then, the partial of P with respect to V at fixed T. Well, P is equal to nRT over V. The partial of P with respect to V is equal to minus nRT over V squared. Of course, you should be able to verify that. Then for the third partial says, take the derivative of the volume with respect to time, the volume with respect to temperature, as the pressure is held fixed. So dV dt at fixed P, since V is equal to nRT over P, I can take the derivative of that with respect to T, and that is equal to nR over P. So when I combine those three, it says that nR over V has to equal negative times minus nRT over V squared times nR over P. Just putting everything together that we have learned. And if I do simplification, as you see I do at the bottom, I do some cancellations of N and R, a couple powers, actually I do a trick there, I do a little substitution in that nRT over V squared is equal to nRT over P over V times nR over V. Notice how I did a little bit of a trick there. Not really a big trick. For V squared, I took the V squared out and I put in V is equal to nRT over P for that one of those V terms. And I get the expression that you see simplifies to show that both sides of this equation are in fact equal. Let's look at an early example of the application of one of these advanced mathematical techniques to the interpretation of a physical problem. And that physical problem was the idea of what we have earlier discussed as being the so-called internal pressure. Internal pressure, we gave the symbol pi t, and I defined it as the change in internal energy with respect to volume in an isothermal process. So if you remember what we claimed was for a real gas, du is equal to c sub v dt plus pi t dv. Now what we then claimed was that pi t must be 0 for an ideal gas. So that for any ideal gas, du is c sub v dt only, because the pi t term is equal to 0. And we phenomenologically made arguments about that because the ideal gas has only kinetic energy. It has no source of potential energy. And since it only has kinetic energy, that energy can vary only as the motion of the particles varies. And the motion of the particles varies only with temperature. So you can change the internal energy of a gas only as you change the temperature. If, in fact, you do go to change the volume while the temperature is held fixed, you're moving the particles closer together, placing them further apart. But since they have no potential energy to begin with, that does not affect the energy of the ideal gas. So pi t phenomenologically is 0 for an ideal gas. Here in a few slides ahead, we're going to be able to prove it mathematically now that we're introducing these new tools. But for now, we have already made several claims that pi t is 0 ideally. Well, Joule decided he was going to attempt to measure pi t for a real gas. So what he did was he put air in a chamber that he jammed up to a very high pressure. He made this real gas air up all the way up to 22 atmospheres of pressure. And then what he did was he sealed it in a container that had a stopcock attached, and he connected it to a vacuum chamber, and he opened the stopcock and let the high pressure gas expand into the zero pressure area, so that he was looking for how the internal energy would change as the volume changed. So he was looking to see if he could detect any temperature change in the bath, to see if he was getting any sort of change in this fashion. So when he opened it up, he detected no change in temperature that the bath was undergoing. So what he then could assume was he was doing an isothermal change in the internal energy as the volume of this gas changed. Pretend we're James Joule and look at how he interpreted this experiment based on the mathematical tricks that were now available. Okay, so since there was no temperature change in the surrounding water bath, there's no heat exchange between the expanding gas and the water, so dq was equal to 0. And since the gas expanded against the vacuum, P external dV with P external equals 0 means minus P external dV was 0, so dW was 0. So therefore du, which is dq plus dW, when there's no heat exchange and no work being done, du was equal to 0. So what he then did was took his expression for the internal pressure, du dV at fixed t, and applied the permuter. Did the mathematical trick. He applied the permuter, and it said that du dV at fixed t, or the internal pressure, must be equal to minus du dt at fixed v times dt dV at fixed u, or it must be equal to how the first term, which he identified as being the constant volume heat capacity, times the second term, which is dt dV at fixed u, which is how the temperature changes with volume under constant internal energy. And again, remember, what he had concluded was there is constant internal energy because du is 0 since there was no heat exchange and no work done. So since there was not a detectable change in temperature as the volume expanded, dt dV fixed u was equal to 0. So the conclusion of Joule was that pi t must be 0 for a real gas as well as it is true for an ideal gas. Joule published this work. William Thomson pointed out to him that, hey, you know what, water has a pretty high heat capacity, and the change in temperature because of that high heat capacity might have been so small that your device was too crude and your temperature sensing device was just not high resolution enough to pick up any of that temperature change, because he believed there should have been an internal pressure value for a real gas. So rather than fight with Joule over this idea, they decided to collaborate over it. And it turned out to be something that both of them worked on for a long period of time. You can see they did experiments on this for a good 10 years where they tried to perfect the experiment and try to measure some kind of change. And they came upon finally a design of the experiment that was done by Thomson himself. By the way, William Thomson was no slacker in his own right. William Thomson was Lord Kelvin. This was just before he was knighted that they did this work. But in any event, he designed a two-piston system. The piston on the left would shove a gas in that was at some measured PV and T values. It would shove it through a porous plug that it could get through, and then as it got through that porous plug, it would push back a second piston. So he maintained this, using the second piston, he could maintain the pressure P2 being greater than P1 at all times, and they insulated the system so that it was adiabatic, so that there would be no exchange of heat from the outside, so that if there was a temperature change, they could measure that internally. So he could measure a P2, V2, and T2 after going through the plug and pushing on the second piston, compare that to the P1, V1, and T1 that went on in from before the plug by the pushing of the first piston. Okay, if we look a little more closely at the Joule-Thomson experiment, here's what we'll find. We'll let the first piston push the gas through the porous membrane, and it's pushing the gas at a pressure P1 that we'll assume is just maintained as a constant pressure, so that the gas is pushing back as this piston is pushing in, P1, and it compresses it a volume of the gas occupying up to the porous membrane. So the work being done on the gas is P1, V1. Then when it gets through the membrane, it pushes back a second piston. That second piston maintains the gas at a lower pressure P2, so that the second piston slides back at that lower pressure, and the work being done by the gas to push that piston back is minus P2 V2, so that the change in internal energy being U2 minus U1, that will be equal to Q plus W, but since this experiment was designed so that no heat was exchanged with the surroundings, Q is 0, so U2 minus U1 must be equal to the work, which is P1 V1 minus P2 V2. Now, if I gather up all the terms that have second as their subscript and all those that have first as their subscript, I get U2 plus P2 V2 equals U1 plus P1 V1, or that H2 equals H1. And what Joule and Thomson decided was that they were doing an isenthalpic process. In an isenthalpic process, the entropy, the enthalpy is a constant. So this is a constant enthalpy experiment being performed, and they are measuring how the temperature changes with the change in pressure during this isenthalpic process. So they defined a variable that relates this, known as the Joule-Thomson coefficient. Mu is how the temperature changes with pressure when an experiment is done isenthalpically. Now, this idea of isenthalpic is also true anytime you do something very quickly, like if you take an aerosol can. This is much like what is going on in an aerosol can. I have a gas at high pressure in the can, and then when I squeeze the trigger, it goes through this, similar to this porous membrane, and it pushes back the atmosphere outside. It pushes back just like pushing the piston of the atmosphere back. So you have a high internal pressure pushing against a lower external pressure. So anytime you spray an aerosol can, you are essentially doing the Joule-Thomson experiment. Now, what happens is that when you do something like this, that the gases are found to cool as they expand. dT, dP is a negative value. So generally speaking, Joule-Thomson coefficients are negative. And you might have noticed this if you take a high pressure aerosol can and you start to spray the gas out of that can, the can starts to feel cool. And it feels cool because you have this Joule-Thomson effect occurring. Another place where you might commonly see this is where you're boiling crawfish and you're using these high pressure LP gas tanks, and you attach it to the burner and it comes out into lower pressure. You're doing very similar to this process. And I don't know if you're familiar with it or not, but I've seen it many times, that the regulator on the LP burner connection begins to ice up. It literally gets so cold that it condenses water vapor out of the air, and you get condensation freezing on the regulator of the crawfish burner. That is a sure sign of the Joule-Thomson effect. You are expanding a gas from high pressure inside to lower pressure outside, being pushed back against that second piston. Again, we can consider to be the atmosphere external. So the gas cools as it expands in these isenthalpic processes. Again, I will say we see it every day. If you've ever run anything pneumatic, any pneumatic tools, they also feel cool when you pump compressed air through them as they drive screws. You can get pneumatic drills to put lugs on tires and things of that sort. These also have these similar cooling effects when you expand the gas rapidly out into a lesser pressure atmosphere.